I welcome you all in this course on mechanical measurement systems. Today we will discuss on force and torque measurement. Now force is expressed, as per the Newton's second law, it is F is proportional to acceleration and F is equal to ma. So in today's lecture we will be discussing force and torque. So this is force and torque is, suppose there is a shaft, right, and twisting moment is exerted on the shaft. Then the twisting moment is exerted on the shaft, that will cause the torque, right. If we multiply force with displacement, F into x, it is work, energy, and if we multiply tau with omega, that is also work, energy. Torque, omega can also be expressed by 2 pi n, right, and this is again work. So torque is equal to output divided, or this is the output, not work. It will give the output in power. It is work per second. So it is going to be power. So torque is going to be the power of the shaft, power transmitted by the shaft, divided by rotational speed of the shaft. But how to measure the force and the work, we are going to discuss here. Force also, yes, force is also expressed in terms of kilogram force. It is in MKS unit. So 1 kilogram force is equal to 9.81 newtons. But in SI unit, force is expressed in terms of Pascal, Newton. Force is expressed in terms of in the unit of newtons, and pressure, any amount of pressure is expressed in terms of Pascal and kilopascal. Even very low pressure is expressed in terms of pascals. For example, suppose for example this room, if I pressurize this room, so pressurization may go up to 10 to 15 Pascal. If you look at the 10 Pascal, it is equivalent to 1 millimeter head of the water, right? So this is the order of the pressurization of the buildings. Nowadays buildings are also pressurized. If the building is pressurized, then dust and all will not enter the building. So the system will remain especially when the building is occupied by the electronic system, there is a lab occupied with the electronic system, it will remain neat and clean. So now we are discussing about the force. We are discussing about the force, how to calculate the force. There are many ways of calculating the force, and there are many reliable ways of calculating the force. First of all, we can use balance. Balance can also be used for measuring the force, because the force against the known gravitational force, and if it is balanced, then we will say that the force is equivalent to that. Suppose on this side we are having 100 kg. This is the known gravitational force, 100 kg force. So 100 newtons. If this balance is this side also we are applying 100 newtons, or the balance, if the balance is, or the arm of the balance is in a horizontal position, or there is no deflection, then this unknown force is also 100 newton. So that is very primitive and very reliable way of measuring the force. Another is transmission of force through a fluid as a pressure, in the form of pressure. The force is converted into the pressure, and this fluid pressure is exerted on primary, let it be any primary sensing element, right. So that is another way of measuring the force. Third way is, suppose there is an elastic member. Suppose there is a bar. I want to use this bar for measurement of force. So suppose the force is applied here. right? When the force is applied here, then force multiplied by the length divided by A into E is equal to X. Force into length, FL by A, because is change in the length of the bar. It is simply case of modulus of elasticity stress upon strain. Stress is force by area, strain is X by L, and from here we got the value of X like this, and this X can be measured here and we can find, so we can have a force as a function of X, or we can say, if we say F is equal to Kx, then here the K is AE by L, a constant, because a cross section area is a constant, modulus of elasticity is a constant, and length is also a constant. Now, like this, we can also make use of a simply supported beam. Simply supported beam can also be used for force measurement, because there is a simply supported beam of length L. In the middle of the beam, the force F is applied, and if we are able to measure the deflection, if we are able to measure the deflection of the beam, delta, and there are many devices to measure this deflection, then we can write the formula, the deflection or X is equal to 1 by 48 F L cube by EI. EI is the moment of inertia of the cross section of this bar along the axis, XS axis. So here F is equal to 48 by L cube EI multiplied by delta or X. And this is also a constant here. So the moment we calculate the delta, we will definitely multiply delta or X by this constant K, and we will get the value of F. That is another way. This is for the basics of the very basic things for the measurement of the force. We can make use of springs also for the measurement of force. F is equal to Kx is a known formula. So there is a closed spring. Closed spring is that spring for which helix angle is less than or equal to 5 degree. When it is more than 5 degree, it is an open spring, right? So let us take one spring, right? It can be an open spring also, right? So let us take an spring and the force is applied. When force is applied on the spring, the deflection of the spring is equal to 8 F d cube n divided by C d to power 4. C is the modulus of rigidity of the wire, n is the number of turns, d is the diameter, spring diameter, coil diameter, and d is the diameter of the wire, right? From here also we get the function displacement as a function of F. So K here will be C d raised to power 4 divided by 8 d cube n. So spring can also be used as a force measurement. A thin ring or probing ring can also be used for force measurement. We have already discussed this type of rings in earlier when we were discussing about the transducers. If the force is applied here and this change in the diameter will take place, and it is a curved beam, so displacement x is going to be equal to 1 by 16 pi by 4 minus 4 by pi d cube f divided by EI. So from here also we can get the value of K, and then we can make use of the formula Kx for finding out the force. So this is the description of force measurement using elastic members. There are load cells also. load cell. And load cell are very popular for the force measurement, and they have variety of applications. So the load cell is used to describe a variety of force transducers which utilize the deflection or a strain of elastic member or increase the pressure in closed fluid. So the force transducers, either they use deflection or strain is measured, that is one way. In a load cell, either deflection or strain is measured, or second thing is when the force is exerted, the pressure is also exerted. So rise in pressure, so there are two ways of force measurement by this load cells. Either increase in pressure due to application of force. The first one is increase in pressure due to application of force, that is one way. Another way is strain develop in the column. Suppose there is a vertical column and force is applied. So whatever strain is developed in this column, if you are able to measure that, that will also help us in finding out the force applied on the column. So they are hydraulic. There are three types of load cells. One is hydraulic. Second is pneumatic. And third is strain type. Now in hydraulic load cells, as I mentioned earlier, the force, through the primary sensing element, force pulse is converted into the pressure, and the pressure pulse is transmitted through the hydraulic pressure to the primary to the sensing element, and the measurement of force is done. And same is case with the pneumatic type of load cells, right? So here we get the pneumatic pressure wave, which is subsequently sensed, and the measurement is done. But the most popular is the strain gauge type of load cells. Now strain gauge type of load cells strain gauges, definitely the concept of strain developed is used here. So there is a vertical cylinder in strain gauges type of load cells, and 4 strain gauges are fixed. This is also known as Poisson's arrangement. This is also known as Poisson's arrangement, and this force, when it is exerted on the cell, the strain is developed. Now in strain gauges, when they are stretched or compressed, there is a change in the output signal, right? Now 4 strain gauges are fixed, and they represent each arm of a Wheatstone bridge. Okay, and the arm is 1, 2, 3, and 4, right? And some input is provided. This is, let us say, is Vs. Okay, and these arms are balanced, so there is no deflection in galvanometer. Now, fixing of strain gauge. How to fix strain gauge on the tube wall or the walls of this structure? So on two opposite wall, they are fixed in this direction along the axis on two opposite surfaces, not wall, opposite surfaces. And on two opposite surfaces, it is transverse arrangement. It is a transverse arrangement. Right? So there are 4 strain gauges. Now 1, 2, 3, 4. Right? So 1 and 4 are along the axis, and 2 and 3 are perpendicular to the axis. Now, we will measure, because this is ABCD. When this bridge is balanced, in that case, potential difference between this and this are equal, because there is no potential difference between this and this, because there is no flow of current. So, VAB is equal to VAD is equal to Vs by 2. This is Vs. And this again, this is true for this also. So, potential difference between this and this is equal to half of the Vs. Now, I will remove this. Now, VAB is equal to current. Current between A and C is Vs by R1 plus R2. This is the current flowing between from C to A. And now we know the Vs by 2 is equal to VAB, right? So, and it is equal to R1 by R1 plus R2 Vs. R1 is, suppose once we have the current, so V is equal to IR. So, this is the potential difference between VAB and VAC also we can AD we can also calculate. AD is equal to R3 divided by R3 plus R4 Vs. Right? Now, the vertical column is put under force. When it is put under force, the strain gauges which are along the axis, they will be compressed, and the strain gauges which are on the diameter, which are perpendicular to the angle, because the diameter will increase, they will come under tension, or vice versa. If the load cell, there is a tensile force on the load cell, then the strain gauge which are along the axis, the resistance will increase. Let us say resistance will increase, and which are perpendicular to the axis, the resistance will decrease, right? So, in this case, when the load applied on the strain gauge, because all the resistance have the same R, this is R, this is R, this is R, and this is R, right? So, when all the same, then we can say this is 1 by 2 Vs, R is equal to R1 plus R2, right? Now, the strain gauge is compressed, resistance has reduced. So, it has become R minus, so VAB is equal to R minus dr divided by R minus dr plus R plus mu dr, right, multiplied by Vs. Okay? Now, the potential difference between AB is R minus dr divided by R minus dr plus R plus nu dr multiplied by Vs, right, and potential difference between AD is R plus nu dr, R minus dr plus R plus nu dr multiplied by Vs. Because now the bridge is not, the equilibrium is disturbed, so we will have a deflection here, and the change in the volume, change in the voltage dVO, the output between B and D is going to be difference of these two. So, difference of these two can be taken here as like this, and so dVO is equal to R plus nu dr minus R plus dr divided by 2r minus dr 1 minus nu. So this r and r will be cancelled out, multiplied by Vs, right? So we'll be getting, this is 1 plus nu dr divided by 2r minus dr 1 minus nu multiplied by Vs, right? Now this can further be written as VO, delta VO or dVO is equal to 2 1 plus nu. Now this is dr, so dr upon r, and then we get Vs by 4, because numerator and denominator, they are multiplied by 4. So because if we take this dr multiplied by 1 minus nu, so this we have neglected here, and then we have got this expression. So if we neglect this, then this is going to be the final expression. So this expression shows that what is going to be the change in the output voltage when there is a dr change in the resistance of strain gauges. Now for further understanding of this, let us solve one example. A strain gauge load cell consists of a solid steel cylinder which has 4 identical strain gauges. This is strain gauges mounted upon it in the Poisson's arrangement. Poisson's arrangement is the same arrangement, 2 along the axis, 2 perpendicular to the axis. For each gauge, the nominal resistance R is 100 ohm and gauge factor is 2. So gauge factor F or G is 2. Resistance is 100 ohms and gauge factor F or G is 2.0. And the gauges are connected elastically to 4 arms of a Wheatstone bridge, I explained earlier, which is energized with the supply of voltage 6 volts. So Vs is 6 volt DC. Right? Make calculations for the sensitivity of the load cell. The steel cylinder is 50 mm in diameter. This is a very common dimension of a load cell, 2 inches, that is 50 mm approximately. And modulus of elasticity for steel is 200 gigapascal and Poisson ratio is 0.3. Now for this we have to find sensitivity of the load cell. So let us take 1 kilonewton of force which is working on the load cell. So sigma is load divided by area. So 1 kilonewton means 1 into 10 to power 3 divided by area pi by 4, 0.05 square, pi by 4 d square, and this will give the stress as 0.5095 megapascal or 0.5095 into 10 to power 6 Pascal. Strain is equal to stress by E. So it is 0.5095 into 10 to power 6 divided by 200 into 10 to power 9, and that is going to be equal to 2.5475 into 10 to power minus 6. That is the order of strain which is developed by the application of 1 kilonewton of force. Now the dr by r, change in the resistance, is equal to, this is FB, F into epsilon, or the G into epsilon, and that is equal to 2 into 2.5474 into 10 to power minus 6, and it is equal to 5.095 into 10 to power minus 6. This is change in the resistance dr over r. Now we can calculate the value of VO, unbalanced voltage. This VO is equal to 1 plus nu dr over r Vs by 4 dVo. Okay, and that is going to be equal to 2 into 1 point plus 0.3, 5.095 into 10 to power minus 6 into 6 by 4, and that is equal to, divided by, this is dr by r. So it is equal to 19.87 into 10 to power minus 6, or 9.87 microvolt. So sensitivity of the gauge is this output voltage, right? That is, we are getting here 19.87 into 10 to power minus 6 per kilonewton. So per kilonewton application of the force, this is the output of the voltmeter which is connected with the opposite arms. So this is the sensitivity of the strain gauge. Now after this we will take up the torque measurement. For the torque measurement, the governing equation is T is equal to IP, this is the governing equation, is equal to shear stress upon R is equal to C theta over L. L is the length of the shaft, theta is the angle of twist, R is the radius of shaft, this is polar moment of inertia, right? And from here we can always calculate the value of torque if we have the value of CIP by L as a function of, so torque as a function of theta, this is the multiplying factor, or torque is also IP upon R multiplied by shearing stress. So both ways we can measure the torque from the shaft. Now measurement of theta is important. If you are able to measure the theta, the torque can be easily measured. So there are certain techniques for torque measurement. First of all is mechanical torque meter. Mechanical torque meter is mechanically fixed to the shaft. So on the shaft there is a marked disc. If I fix a rod parallel to the shaft on the surface of the shaft, and when the shaft is twisted, right, the indicator will indicate the reading on the marked disc, and from where we can calculate the value of theta. Length of the distance between the indicator or the length of this pointer is known to us, value of C of the shaft is known to us, modulus of rigidity, we can find the value of torque exerted on the shaft. So that is the mechanical method of torque measurement. There are optical methods also. In optical methods on the shaft, I mean there are two fixtures. Now optical methods, you can measure the lateral thrust also on the shaft, and one optical measure, this is the transmitter, and this is the optically sensitive receiver, and this is one, and this is optically sensitive receiver. So when the torsion takes place, we know the length. There is going to be the lateral displacement between these two, right? Now this lateral displacement can always be correlated with torque, because in the measurement most of the signals are converted into the displacement. So one is fixed here, another is fixed here. When there is a lateral displacement or an alignment of this arm and this arm, this is the displacement x, and this can always be correlated with t. If there is a lateral thrust, then they will move over each other in this direction. Then we can find the thrust or lateral thrust also. So that is another technique, which is optical technique for torsion measurement. For electrical torsion measurement, there are two discs and there are two transducers. In fact, there are two magnetic discs or slotted disc fixed on the shaft. There are two slotted discs fixed on the shaft, right? And we get signals from both the discs. The signals are received from both the discs. And when the shaft rotates, we get pulses from this disc. So from a single disc, pulse will give the omega. And pulse difference between, time difference between the pulses between two discs can be always be related with torque. And if we take multiple of these two signals, then we can find the power also, because power is T omega. So this is how the torsional meter is used, electrical torsional meter works. And that is all for today. Thank you very much.